Hello, and welcome to Virtual Investor Conferences. We're very pleased you joined us for our quarterly Small Cap Growth Conference. Our next live presentation is from BTQ Technologies. BTQ is an innovative leader in the quantum technology and digital security. Please note you may submit questions and view a presenter's availability for meetings by clicking Questions and Book Meeting tab in the top toolbar. At this point, I'm very pleased to welcome Nicholas Rusey-Newton. He's the co-founder and Chief Operating Officer, Nicholas?
That's right.
Of BTQ Technologies Corp, which trades on the OTCQX Best Market under the symbol BTQQF and on CBOE under the symbol BTQ. And I'm thrilled to note that BTQ was the top performer on the OTCQX marketplace in 2024. Welcome back, Nicholas.
Thanks, John. Great. Well, great to be here. As John mentioned, I'm co-founder and chief operating officer of BTQ Technologies. We're a Canadian company that's focused on securing mission-critical networks with near-term quantum technologies. So there's a lot of excitement in quantum technology right now, but this is really decades in the making. And people are excited about this new computational paradigm as it relates to classical computers. So classical computers employ bits to encode digital informations as zeros and ones. Quantum computers, on the other hand, use quantum bits or qubits. And qubits also encode information into zeros and ones, but without the constraint of being strictly one or the other. A qubit may be an arbitrary superposition of the two, where the two values have different weightings. And these weightings are known as quantum amplitudes, given by complex numbers. And quantum computers achieve advantage by exploiting these degrees of freedom, which do not exist classically. And there's a lot of motivation for building these quantum computers, not only because they'll outperform conventional computers in terms of speed, but they also represent an energy advantage or kind of increased energy efficiency over existing supercomputers. It is still difficult to build these systems today, so the quantum computers we have are small scale. And the reason for that is qubits are very fragile when they're measured or interact with their external environments. So as quantum computers develop and this industry develops, there's going to have to be robust quantum error correction techniques developed to enable the scaling up of these devices. But yes, as mentioned, this is a long time coming. Quantum computers have been developed for decades now. So D-Wave Systems, the first company to build a commercial quantum system, was founded, I believe, in 1999. So there's now been decades of research, and on the back of this recent announcement by Google in December, the Google Willow chip, there's now a lot of excitement in the space by large companies and governments. And you also have NVIDIA recently announced a large quantum technology event at their upcoming conference. So from a commercial perspective, why companies are looking into quantum technology is this idea of quantum supremacy or quantum advantage. So being able to solve certain problems quantum mechanically that we can't do classically. And this is an upcoming milestone that everyone is looking at in terms of benchmarking and achieving. And quantum advantage is the solution of a problem using a quantum computer faster, cheaper, more efficiently than any available classical solution. There's no kind of claim to this today, but we're seeing actually some promising areas at BTQ where there are potential demonstrations of quantum, near-term quantum advantage. Even though in the community, the status quo is that we're still going to have to wait for these very large-scale quantum computers that have millions of qubits to really solve any useful problems, especially as it relates to the most famous or infamous problem of breaking cryptography. But we are seeing a lot of progress as it relates to quantum computers and cryptography. And quantum computing companies, not just the large tech companies like Google and others, but there's now a flurry of startup quantum computing companies, and they are all benchmarking against cryptography in terms of the advancements they're making as it relates to breaking that underlying math problem. And just the other day, actually, a startup, I believe out of France, called Alice and Bob, published a paper which suggested using their architecture that they could break RSA cryptography in 7 days with less than 100,000 qubits. So that seems to be a huge breakthrough advancements under the radar for sure. But we're now seeing these types of developments almost every day. And just to put that into perspective, I believe some groups in New Mexico have already demonstrated, I think, around 6,000 qubits. So kind of 100,000 or 90,000 qubits isn't that far off if you really think about it in terms of scaling these systems up. So the impact that quantum will have on the internet is far-reaching, and it's already happening. I was recently traveling in Korea and Japan, and all of these places are building large-scale quantum networks across their countries. This is laying dedicated fiber that can send quantum information, and it can run interesting applications today, such as QKD or quantum key distribution. This is a type of data security that has what's known as information theoretic security guarantees. So this is not based on computational assumptions, in that an increase in computational capacity won't add additional vulnerabilities to these systems. But they're secured quantum mechanically. So it's a greater level of security, and that's being used to, in Switzerland, for instance, to secure the Swiss election. So you're now seeing these build-outs of these quantum networks, and you're seeing overlap and hybrid applications with the existing internet. And that will only continue as the technology improves. So going back to some of the most famous applications for quantum computers, so they are going to be exponentially faster once realized, and there's a whole space now of quantum algorithms, researchers looking at what can we specifically devise to run on quantum systems. And the catalyst behind this was Peter Shor back in 1994, who developed Shor's quantum algorithm. And this was a way to break large numbers into their prime factors faster than any existing computer. So you could look at what would take a supercomputer today thousands of years. That could take literally hours or days with a quantum computer. And Peter Shor was able to theoretically demonstrate that. And that was a huge catalyst for one, how do we secure information in a quantum age? But how do we build these quantum systems as well? And in addition to that, there's been a huge amount of government standards and funding that have been introduced on the back of all these discoveries and advancements, led by the US and China. In Canada, you also have the National Quantum Initiative that was introduced a couple years ago, which introduced, I think, around $500 million, which is now being allocated to companies like BTQ. You're seeing new funding announcements almost every week. We have a presence in Australia and a partnership with some of the universities there. And there was just recently over $1 billion allocated to a single company, PsiQuantum in Queensland. So a lot of countries that have background in funding quantum science are really doubling down as they see the exciting commercial opportunity to build their own quantum sectors. So BTQ has been in the works for almost a decade now. So started this with my older brother, Olivier. And this was about the same time that the US government started this standards process to upgrade cryptography for the quantum era. So at the time, there were a number of companies that were already looking at building quantum computers, but very few looking at, okay, how do we leverage kind of quantum algorithms and near-term quantum technologies, and how do we also develop new cryptographic standards that could be secure? So we started developing intellectual property around these quantum cryptography standards, started looking at building university partnerships, because that's where most of the talent is. This is a very small talent pool globally as it relates especially to fields like QEC or quantum error correction. Sometimes you're talking literally hundreds of experts globally for some of these problems. We also started working with government institutes in Canada and in Taiwan and Australia, as well as the standards bodies themselves. So we were involved in the NIST standards process, the US government standards process in terms of designing algorithms. This enabled us to be at the bleeding edge, and again, to also work with all of the top researchers in the space to develop this highly specialized intellectual property. And as it relates to corporate partnerships, so there are a lot of companies now interested in quantum intellectual property. So as it relates to what BTQ actually does, so we both kind of work with large companies and co-develop IP in tandem with them. We develop our own products and quantum-related intellectual property. And we also engage in government projects and standards. And in addition to that, we've been recognized through journal publications and other recognition. And we've also been building a substantial patent portfolio around this. So a lot of the near-term focus for immediate use case has been around security, cryptography. This is an area we're very excited about. And there's a huge catalyst for widespread adoption just because these are now mandated by the US government and other governments. So after that 10-year process started this past August, a series of algorithms were standardized. And the year before, the Biden administration enabled this through various executive orders. So now there's a pressing concern if you're a large corporate or government, you have long-term data security requirements and you need to be encrypting information with quantum secure schemes. And the reason why there's so much urgency around this is one, these standards are mandated, but two, there's the risk of adversaries storing data today and just decrypting later if they have a long enough time horizon. So that's why it's important to be securing information with post-quantum schemes today. And also, this just takes a huge amount of time. So these transitions historically take about a decade, and that could already be within the time frame that someone develops a scalable universal quantum computer. So as it relates to this next generation of cybersecurity, what we have to transition to is not a straightforward transition. We have to adopt algorithms that have new mathematical foundations, and these are typically much larger in size, larger key sizes, larger signature sizes, and we need to develop new hardware architectures. We need new implementations within software, and has to be optimized for various different use cases. So this is a very large undertaking that's kind of currently taking place and will only accelerate. So we've looked at hardware from a post-quantum first lens. So you can think of all the connected devices that employ cryptography. So whether that's your car or your phone, or whether in digital currencies as well, there's a need for hardware architectures that compute these new, larger algorithms very efficiently. So that's why years ago we started looking at an architecture called processing in memory, or PIM, which was widely in use in the artificial intelligence field, but no one had applied that to kind of crunching these NTTs, or theoretic transforms, that are the main mathematical underpinnings of these post-quantum algorithms. So we started looking at developing hardware, specialized chips, implementing this technology. And this technology could be used within our own dedicated chipsets, or we can license this to other hardware companies to incorporate in their own chips. And we recently doubled down on this approach through the acquisition of a Stanford company called Radical. So Radical had a similar insight several years ago when we started as well, that this processing and memory architecture that was developed to apply within the AI industry was very effective at computing post-quantum cryptography very efficiently. So we've onboarded their leadership team to BTQ, and we've also kind of their customer relationships and their intellectual property portfolio. And we've developed out and are developing an offering around what's known as soft IP. So this is almost like software that we can license out to companies that want to incorporate post-quantum standards within their hardware offerings. And we'll also move to hard IP offerings, or chiplet offerings, and secure elements at a later stage. So another area we're very excited about is just looking at these NISQ era quantum devices. So NISQ would be referring to near-term intermediate scale quantum computers. So these are the quantum computers that are readily available today that have perhaps hundreds of of qubits. And again, the industry hasn't found many use cases for them, but we're actually very excited at BTQ about what we can do with these near-term devices. So we've invented a series of different quantum algorithms. One of them is our quantum proof of work, or proof of work by consensus by quantum sampling. And what this does is it is a proof of work analog. So proof of work being the consensus mechanism within Bitcoin or other digital currencies. And this as opposed to using existing computers, we use quantum devices or boson sampling devices. So this is a non-universal quantum device that's commercially available today that you can purchase from companies like Xanadu or other photonic quantum computing companies. And we devised a way to include them in performing validation within a consensus paradigm. And why that's exciting is, one, it's a clear use case for near-term quantum computing, but we also were able to demonstrate a quantum energy advantage. So there was a significant kind of energy efficiency performance gain using these quantum devices while also being quantum secure. So huge benefits as it relates to deploying near-term quantum algorithms and technology. And this was a large undertaking, multiple different universities involved. And we recently had a journal acceptance based on this research. Another application we're excited about is this area known as one-shot signatures. So digital signatures are ubiquitous on the internet and within cryptography. And one-shot signatures are actually, it's a hybrid approach to leverage a quantum computation with the generation of those digital signatures to basically leverage quantum properties such as the quantum no cloning property, where you can kind of mathematically guarantee that a message would only be signed once. So there's a lot of use cases for this technology within just core internet infrastructure or within blockchain environments as well. And the quantum hardware that would be required for generating these is relatively, in our view, near term. So that's another area where we're seeing a lot of exciting applications, near-term applications within cryptographic infrastructure. So as it relates to working with large corporates, we have an engagement with Hunhai Foxconn, where we're developing quantum IP. So we're very excited to be working with them on Prion. So Prion is a digital signature standard, post-quantum digital signature standard that we authored that was shortlisted by the NIST agency. We also received funding from the Canadian government to do further research and to implement this within hardware environments. And we're very excited about working with other companies as well, like our partner at IDQ in Korea. And we see this as great synergistic partnerships, especially as it relates to these companies that have technology that we can leverage and so forth. So in Canada, in terms of our university partnerships, we're very excited to be working with the University of Waterloo. So we're part of the Cybersecurity and Privacy Institute there. And Waterloo is the #1 quantum institution globally. So it's a huge national asset. There's still only a handful of companies working with researchers there. and working on government projects. So we're very excited about this partnership and our recent funding that we're working with them on as it relates to expanding cryptographic infrastructure around Prion. So just to go over the team, we have a deep bench of PhDs and quantum researchers, which these are relationships we've been building for years. So I'll single out a couple. Prof. Brennan, who's the Director of Quantum Engineering at Macquarie University. He is the director of our Australian subsidiary. And also Professor Kohei, who's at Kyoto University, who helps our post-quantum cryptographic research. So these are, again, relationships that we've built over years. And in terms of talent, we're very lucky to be working with these highly distinguished researchers and professors. So with that, I'll leave it there, and I think I can turn to the Q&A to see if there's any questions on the presentation. So there's one question here: when will quantum be commercially viable for business? So the post-quantum security, cybersecurity is mandated currently. So you have a lot of companies that are now required to transition to that. So that's a clear opportunity. And as it relates to harnessing quantum algorithms and near-term quantum devices, I mentioned 2 products of ours around quantum proof of work and one-shot signatures. And we believe those are also kind of relatively near term in terms of commercial viability. And another question, is BTQ equally involved and technologically invested in the AI sector as well as quantum? So this is very interesting. We've been watching a lot of the activity as it relates to all of these AI chip companies, just because a lot of them are interested in having post-quantum security. So that's something where is a great potential opportunity for our QSIM hardware IP offerings. So that's an area we're certainly very excited about. So as it relates to other companies developing hardware, what is the differentiator? So we're not aware of anyone who's also developing processing and memory-based hardware for post-quantum cryptography. So in that respect, we would be the first mover in that regard. Great. Well, I think that leaves it there. So yeah, thank you all for the time, and please reach out if there's any questions. We're just BTQ, btq.com, and thanks so much for the time.